Okay, let's look at work. So, work is mechanical energy that can be added or removed from a system. And we do this, through some force. So basically, if we consider that E represents the amount of mechanical energy or energy itself that we have in a system, okay? If we want to increase that mechanical energy, we can use a force to add mechanical energy. If we want to remove some energy, we can use a force to take some of that energy away. Generally, what we see is that we take a force and we point the force in the same direction that the object or the system is traveling. We do positive work. And this makes sense because if you push something in the direction that it's going, it's probably going to go faster or it's going to gain more potential energy. If we use the force against the motion, such as a force like friction, we tend to remove energy from the system and the mechanical energy will decrease. So again, mechanical energy added or taken away from a system is what we call work, okay? And work doesn't happen by itself. Work is done by something in the environment on the object of interest. For instance, a car. We take the chemical energy from the combustion of gasoline and air. This creates thermal energy, which then causes the gas inside the cylinders to expand. They then do work on the engine. The engine then does work on the wheels. The wheels do work on the road, and our car goes forward as it applies a force on the road to propel itself. So again, work is, energy added to a system, mechanical energy added to a system. Now, the equation for work is really quite ugly, okay? Well, I guess that's unfair to call it ugly, but it's quite complicated. And unless you've taken calculus, the most general form is actually really difficult to understand. It says that the work is equal to the integral of the dot product, remember dot product, or the scalar product, the dot product of the force times the infinitesimal amount of displacement. Oh, that sounds terrible. Okay. We want to take a look at some more specific cases that are simpler before we really get crazy with this particular integral right here. Most of what we're going to do when we deal with a complicated force is we'll graph that force, and then whatever that force is as a function of position, we'll take the area underneath it, and that'll help us calculate the work for these more general situations. Let's see if there's an easier equation to use for work. Well, we can reduce the dot product using cosine theta, but that doesn't really make this so much easier. I mean, again, we're still relying on calculus to do this integral here. So we're still dealing with a fairly nasty equation right here. However, if we can take a constant force and, okay, say we take a force, f dx, and f is constant, we can put the f outside the integral, and the integral just simply goes away, okay? Well, it doesn't really go away, but basically what happens here is if the force is constant and we integrate over some distance over that force, f being a constant is unchanged, and our integral just becomes delta x, or delta x times cosine theta. All right. Most of the forces that we deal with are going to be constant. We saw that in the dynamics problem when we had a constant net force and that led to a constant acceleration. So there are many cases that we get lucky and we can reduce it to that. And in that particular case, work becomes how much force we place on the object, how far the object is pushed. Delta x represents the displacement in some direction. And then this cosine theta comes here because it is only the component of the force which pushes the object in the direction that it's traveling that is going to add energy to the system. Okay, think about that. If I put a force in a direction that the object is not traveling, it's not going to change its speed. Okay, only the component that is in the direction of motion is going to add or take away, if it's in the opposite direction, energy from the system. Okay, what is the simplest form that I can come up with work? Well, oftentimes I just tell people to start out and just start out thinking work is force times distance. Work is force times displacement. After all, if we remember the joule is equal to 1 Newton, how much force, times the meter, how far we've gone, and that pretty much fits in well with this equation that we have right here. So if we push an object or we pull an object with some force, and we push in the direction that it's traveling, the total work that we do will simply be the product of the force and the displacement. Just one-dimensional motion right here. Okay, so that's the simplest form that we can get. If the force is not in the direction of the displacement, well, then we got to go back to this cosine theta. Okay, what if the force is pushing in the opposite direction, as is in the case of friction? Well, if we think about this, the cosine, okay, of 180 degrees, because friction is pointing this way and the displacement is pointing this way, so there's 180 degrees between the two. The cosine of 180 degrees is -1, okay? So when we do work here, work is equal to negative force times displacement. And friction, as we know, will take mechanical energy out of the system and simply turn it into heat. Usually turns it into heat. Okay, let's do some calculations. But before we do this, again, we can just think of, again, work in the most general sense as sort of being the product between force and displacement. You lift up a very heavy mass, you'll need a certain force to overcome gravity, okay? How far you move it times the force will be our work. When you're throwing something, such as the case of a shot put in this field sport or throwing the javelin, you don't just, give it a chuck. You actually use very specific motion. The shot put thrower will actually rotate their body in sort of a helical path and then release the shot put. The javelin thrower won't just throw the javelin from the foul line. They'll run up to the foul line and get up as much energy as possible before releasing it. That's because work is equal to force times distance. If you can maximize the displacement, you can maximize the velocity. Same thing with throwing a baseball, same thing as throwing a softball. All right, just showing you a simple calculation. And again, remember, the actual general form for work is very, very complicated. It's this awful equation right up here. But in most cases, we can simplify this. If f is constant, the integral goes away. If f is pushing in the same direction as a displacement, okay, the cosine goes away. So most of the cases are actually special that we look at. In this case, we'll look at a special case. We're going to look at a car engine producing 250 newtons of force. the car is going to travel 3,000 meters, and with a constant force and a force in the same direction as the displacement, our equation just simply becomes force times displacement. So I have 250 newtons, okay? Convert my displacement into SI units, so 3,000 meters from 3 kilometers. And as you can see here, the total work done in this process is 750,000 joules. All right, simple calculation. And again, force is a vector, displacement is a vector, but really we're taking the dot product of a vector, okay? Dot product is also known as a scalar product. You put two vectors in, force and displacement, you get a scalar out. In actuality, if you think about it, we're not really even putting two vectors in. We're putting in the magnitude of two vectors, okay? All right. So again, work gives no information about the time it took for the displacement to occur, okay? So there's no acceleration, velocity, position type thing going on. We obviously, because of this, don't know the velocity or the acceleration of the object. And again, we're also limited in terms of the fact that it's a scalar quantity. So, you know, direction really doesn't have any meaning here, okay? In some cases, the simplicity of using a scalar makes it easier to come up with an answer. The math is much simpler. However, some details of the object's motion are going to be lost because we've lost the vector nature of what we're doing right here. So there's positives in that the calculations are easier when we use energy. There's negatives in that we're losing some of the details that we had. We just dealt with forces. Again, SI units for energy are joules, but that's the SI unit for work. Ergs for the CGS system, and if you want an equivalent, I believe 1 joule is equal to 10 to the 7 ergs. How do we get this? Well, if you look at this, we don't really use CGS units very much, but this is kind of fun to do. We know that the joule is kilograms, meters squared over seconds squared. So to get to 10 to the 7th, we convert kilograms to grams. So that gives us a factor of 10 to the 3. I hope this comes out. We convert meters to centimeters. So that's squared. So 10 to the second times 10 to the second. And there's our conversion, 10 to the 7th difference. The joule is a much bigger unit than the erg. For US customary units, the foot-pound, gosh, I don't even know what the conversion is for that. You know, a pound is a much larger unit of force than the Newton. The foot, of course, is a small unit of movement than the meter. So, you know, putting them both together, my guess is the foot-pound is slightly more than a joule, but we really don't use that. It's confusing because a foot-pound actually becomes the unit for torque later on, and torque is different from energy. Okay, more about work. Once again, when we're moving in the same direction as the force, or the force is in the same direction as motion, we can just use work is equal to force times distance, because the cosine just becomes 1, okay? When the angle between the two vectors is 0, we get 1 there. When the cosine is set to 180, as was the case for friction, friction is pushing against motion, then it becomes -1. Now, for a force that is perpendicular to the direction of motion, when we take the cosine of 90 degrees, we get 0. What that means is the work done by a force that is perpendicular is always going to be zero. That means if you got a diagram like this where you have got the force up here, you got the velocity over here, and making a 90-degree angle, work is zero in that case. And that's important because if you think about that, it makes sense. On a tabletop, if I got a little box right here, it's the table that's pushing up on the box, creating this normal force, right? If the box starts sliding, that normal force can't give it any energy. All right, that wouldn't make any sense. If we're moving this way, the normal force couldn't make it go faster or slower in the direction it's traveling. Therefore, it can't give any mechanical energy due to the fact that it's at a 90-degree angle. So again, work can be positive, work can be negative. It's positive if we're adding mechanical energy, as is the case where we're pushing in the direction it's traveling. It's negative, as is the case for friction, where we're pushing against the motion, trying to slow it down. But as we said, simply applying a force perpendicular to the direction something's traveling doesn't mean any work is being done. Now, this is anti-intuitive. Think about carrying a heavy bucket of something. If I carry it across the room, I'm definitely going to expend energy to carry it. But it doesn't mean that that energy was expended creating work. My muscles need the chemical energy to keep firing and to keep applying attention on my muscular, my skeletal muscular system to carry that. But in actuality, what happens is the energy that they expend does not do any work. That energy is converted simply into heat. Okay? So again, force up against the force of gravity. I walk at a constant rate. My energy is not increasing or decreasing. Okay? Just simply holding it up doesn't do work on it. So again, look at these different cases that we have right here. I have all these different cases, and we're going to say our displacement is horizontal. We're moving in the positive x direction. What should my work be for each case due to that force? First case is easy. Work is zero because it's perpendicular to the direction it's traveling. For the second case, it's going to be negative because notice the force is pushing in the opposite direction from where I'm traveling. Case C, the work is going to be positive because I'm pushing in the same direction it's traveling. And in case D, the work is going to be negative because there is a component in that negative x direction, right? But it's not going to be quite as negative as it was for this case right here. So lift the box up, you're doing positive work. Why? Because you're lifting upward and your displacement is upward. Lowering the box, however, would be negative work. In fact, there are exercises which are called negative reps. And what they're talking about is when you're lifting something up, your work is going to be positive. When you put something down and let the box work against your muscles, then that becomes negative. All right, let's do a calculation here. Here we have an Inuit fisherman returning from a successful fishing trip. They have loaded their sled with salmon. The total mass of the sled is 50 kilograms, and the fisherman exerts a force of 120 newtons on the sled by pulling a rope. How much work does he do if the rope is initially perpendicular to the ground? So that would be a force in this direction. And then if the force were at a 30-degree angle, as is actually shown in this diagram. All right, let's do our calculations. Again, we are going to use the fact that the force is constant. So we can say work is equal to F cosine theta times delta x. Okay, we don't have to use the integral. Nothing crazy like that. We're using the specific case where force is constant. That will be almost always the case for our problems. Force is constant. All right. So we're given the mass, we're given the force, we're given displacement, we're given the angle, okay? Now for the first case, it's very simple. Work equals force times distance. Pull on it with 120 newtons, move 5 meters, 120 times 5, 600 joules. However, when I go from pulling it horizontally to pulling it at a 30-degree angle, now the cosine of 30 degrees is not the same as the cosine of 0 degrees. Cosine of 30 degrees, although not that much less than 1, is now down to 0.866. So pulling with 120 newtons for 5 meters, that'll change the total work to 520 newtons as opposed to 600 newtons. Okay, so you can see how that cosine has changed the actual work that's being done. Let's make this a little more difficult. Let's also introduce friction. Let's say friction has a coefficient of 0.200. Okay, so now I'm going to do work pulling it in this direction right here, but friction is going to do work against me. All right, so I'm going to do positive work. Friction is going to do negative work, and we're going to see what happens. Okay, first of all, what do we need to do? Well, we need to calculate the normal force. Remember, I'm pulling on the sled with a force at a 30-degree angle. So that means that this force does have some vertical component to it, as well as a horizontal component. Okay? Oh, well, we'll do the first case first. We'll do it when there is no vertical component. I'm jumping ahead of myself. Calculate the normal force. The normal force is equal to the weight, 491 newtons. We multiply that times the coefficient of friction, and voila, we have 98.1 newtons of frictional force pulling against us. Okay, what is the work done by friction? We take the force times the displacement, still moves 5 meters, nothing's changed there. And note it's negative 491 joules, because the friction is converting some of the mechanical energy into heat. The work I do is no different, still 600 joules. And if I take this, I add it to this, I see that the net work done on the sled is much less than it was before. Now it's only having 109 joules added to it, as opposed to 600 joules. Gets even worse, even more complicated. For the 30-degree angle, now the normal force, this is where I got ahead of myself. Here's my applied force. It's got a y component to it, so I've got to include this, this, and this in the normal force calculation. Whereas my normal force used to be 491 newtons, now with that slightly upward force, my normal force has dropped to 431 newtons. Calculate the friction, this times the normal force. Now I'm down to 86.2 newtons. All right, so let's do our work calculations. We calculate the work done by friction. Okay, here's my smaller force times my displacement. So I've got negative 431 joules acting against the sled. Here is the work that I perform dragging the sled, 120 newtons, 5 meters, cosine 30 degrees, because again, I'm doing this at an angle, folks. And now I see, once again, that the work that I put in is now down to 520 joules. Now, what is net work? I put in 520. The friction takes out 431. I'm left with 89 joules of work being done on the sled. Okay, so This is an interesting problem in that it combines what we've already learned from statics and doing dynamics problems, and it combines that with our concept of work. Okay, now the ugliness. What happens when my force isn't constant? What happens when the force is varying with time? Well, then I've got to use the definition of what an integral means, or an antiderivative means. What it means is when I take the integral of something, is if I'm taking the integral of a function as a function of some independent variable, in this case it's x, then I say the integral is equal to the area underneath the function, okay, from the initial starting point to the final point, okay? So we see this integral, since many of you might not have taken calculus so far, when you see this integral, think about this integral as saying, take the area underneath the curve. So with a time varying force, for a varying force, will vary with time, but for a force that varies with displacement, more importantly, we can still calculate the work being done, but we need to find the area underneath the function. Here's an example. Hooke's law. This will become important when we talk about the potential energy due to elastic objects. In Hooke's law, the force is proportional to the spring constant times x, the displacement, which means the force will depend on displacement. Oh, okay, here's one of these varying forces. It's nice, however, because when I graph this, the force of the spring is linear with respect to displacement. So when I want to calculate the area underneath this force, what shape is that? Well, that's a triangle. And we know for a triangle, the area is equal to 1/2 the base times the height. All right. So in the case of a Hooke's law, in the case of a spring, we can do our integral, okay? If you've done calculus before, you know if I integrate x dx, I get 1/2 x squared, okay? In the case of this triangle right here, the area is equal to 1/2 the base times the height. In this particular case, 1/2 the base is 1/2 x. The height is kx, and that gives me 1/2 kx squared. X times x is x squared. Pretty cool. So that wasn't too bad. Once we knew how to do it, we could use the definition of work to find out the work done on a spring. Okay. Let's apply this to archery. For many years, the longbow was a very important military and hunting tool. The longbow was basically made out of flexible wood part and then a string made out of some strong, not quite sure what they used to use. They might have used catgut for that, which isn't, is the collagen typically extracted from the intestines of livestock. It has nothing to do with cats. But in any case, you'd have a strong string, a strong bow, which was flexible, and that would create a fairly powerful way to launch or do work on an arrow to project it through the air. Eventually, they figured out that if you curve the flexible material backwards in this recurve bow, you could get an even greater amount of work done on the arrow. Eventually, this transformed into the modern hunting bow, which is a compound bow, which uses pulleys and is similar in geometry to the recurve bow. Now, if we compare the longbow to the recurve, if we compare the longbow to the compound bow, we see for a typical displacement, let's say that I can pull back on it with about 200 newtons of force. Okay, about 200 newtons of force. All right. This is the area I get underneath the curve for the longbow. So this is how much energy I can put into the bow and then get out for the arrow. However, with 200 newtons, look how much force I can get. As I displace it, I never go over 200 newtons, but yet the area is so much bigger. So the reason why the compound bow is so much more effective for the same strength is that it can transfer much more energy to the arrow, okay, than the typical, longbow or recurve bow. And again, it does this through these specialty pulleys. You can see these cams right here, which actually rotate and vary the force. And this gives the bow the ability to keep the force fairly constant as you displace the arrow backwards and displace the bowstring backwards. So you never have to exceed more than a certain set amount of force. And again, compare the two areas. The red area represents the typical amount of work you'd get from just a long bow or from a recurve bow. The red plus the green represents the additional, I should say the green represents the additional, represents the total energy that we can put into the arrow, and you can clearly see it's many times greater. Again, thinking about work and what we're going to call non-conservative forces that act in the opposite direction of where the object is going. We know that in the case of friction, we're doing negative work, okay? When we do work here, we are acting against the motion. Friction is pulling against what we're trying to do. And that must mean that the energy is going to end up someplace. And of course, that energy ends up being turned into heat.